Yeah, so this is number 10 from your multiple choice packet. So the limit as x approaches negative infinity of 2 to the negative x over 2 to the x. And so we could rewrite this if we wanted to by moving this negative exponent down here or moving the positive exponent up here. Either way, it doesn't really matter. So you have a preference on bringing the positive exponent up and making it a 2 to the negative 2x, or bringing this one down and making this a 2 to the 2x in the denominator. Doesn't, like I said, doesn't matter.
Just put it in the denominator. That way they're positive.
Okay.
Yeah.
So we've got 1 over 2 to the 2x now, as x goes to negative infinity. Well, as x goes towards negative infinity, this ends up becoming 2 to the negative infinity. Right? And so 2 to the negative infinity would bring that back up to the numerator effectively, right? This is 1 over 2 to the negative infinity, which is effectively 2 to the positive infinity, which tells us that it is infinity. And I don't know, what were the multiple choice answers there? Was infinity one of them, or was it?
Yeah, probably infinity was one of them.
Yeah. Yep. Does that make sense?
Yeah.
Okay. Cool. All right. So then we got number 20. So number 20 was the limit as x approaches infinity of x times the sine of 1 over x. And so this one, I had somebody ask me about this one the other day. Normally in these packets, I'm not sure why they didn't indicate that this one was a BC only question, but it might, maybe they've changed things and I wasn't aware of it. But this, when you plug in infinity to this, you end up with infinity times the sine of 0, which is 0. And so there's sort of a discrepancy there between infinity times 0, right? We know that, well, infinity times anything should be infinity, but 0 times anything should be 0. So what are we going to do with that, right? 0 times infinity is another form of indeterminate that I guess maybe you should know now. So 0 times infinity is a third type of indeterminate form. So we have 0 over 0, infinity over infinity, and 0 times infinity. Unfortunately, 0 times infinity is not set up as a fraction, so it's not set up as something you can use L'Hopital's rule for. So generally what you have to do with anything that is 0 times infinity, and I would be doubtful that they would give you one like this on the AP test, but just so we know what to do, what we want to do is make a U sub. So we're going to let U equal 1 over x. And so the reason we're going to do that is because, for one, it turns this into, I'm still going to write the limit as x approaches infinity for now, of x times the sine of u. It gets rid of this 0 that we have. But how could we rewrite x? X could be rewritten as 1 over u. And so I could replace this x with 1 over u, which turns it into this nice form that we are very used to, right? Sine u over u. And if we have a limit as u approaches, if u is approaching 0, what would this be? Should be 1, right? And conveniently, that's what we end up with, because if x is approaching infinity, u is approaching 1 over infinity, which would be 0. So we end up with the limit as u approaches 0 of sine u over u, which we have memorized as 1. Or if we don't have it memorized as 1 like we should, you can just use L'Hopital's rule on it and get cosine u over 1, which would be cosine of 0, which would be 1. Does that make sense?
How did you get sine u over u?
Well, I let u equal 1 over x, so that 1 over x became u. And then if u is 1 over x, I just cross multiplied to get x is equal to 1 over u. And so the x becomes 1 over u, the sine 1 over x becomes just sine u, and 1 over u times sine u is sine u over u.
Got it.
Anybody else have any questions on any of the ones on those first 21, right? Was that the first half? All right, number 19. Okay, what was number 19?
It was the limit as x approaches 0, and it was absolute value of x over x.
Approaches 0. Was it from the left or from the right, or was it a two-sided limit?
It didn't say.
Okay, so yeah, two-sided limit. Then if it doesn't indicate with a little plus or minus, then it's a two-sided limit. And so this is one of the ones where it becomes indeterminate, right? 0 over 0, and we don't really have a good way to take the derivative of absolute value because for positive values and for negative values it's different. So what we have to do here is we have to sort of think about what is this. We can one, think about what this function is doing, and that should give us our answer really easily. So if we plug in any x value that is positive, what are you going to get? If you plug in 7, you're going to get 1, right? If you plug in 2, you're going to get 1. If you plug in 1, you're going to get 1. What if you plug in 0.00000000001 for x?
You get 1.
You should be getting 1, right? So I should always be getting 1 here if x is positive, but at 0 I'm not. And then if I plug in a negative number like -7, what should I be getting?
-1.
-1.
Yeah, I should get -1 because the absolute value of -7 should give me 7, and then divided by the -7 should give me -1. And no matter what negative number I plug in, whether it's -7, -pi, -0.000000001, I'm always going to get -1. And so if we were to sketch the graph, it would look just like what I've got there. And we would note that from the left, the limit is -1, and from the right, the limit is 1. And since the limit from the left does not equal the limit from the right, we would say that this limit does not exist. So that's one way to go about this one. The other way would be to say, well, let's actually, algebraically find those limits. So we're approaching 0, but absolute value of x, if absolute value of x, if x is greater than 0, absolute value of x equals x. But if x is less than 0, absolute value of x is the opposite of x, right? That's the definition of absolute value. Technically, that's greater than or equal to 0, but we can't plug 0 into this function. And so we would say then that the limit as x approached 0 from the right of absolute value of x over x, since we're approaching 0 from the right, x is always positive, so absolute value of x equals x. And then that just becomes the limit as x approaches 0 from the right of 1, which is 1. And if we were to do it from the left-hand side, we would note that all of the x values that we're plugging are negative. So the absolute value of x is -x over x. And then we'd say we're looking at the limit as x approaches 0 from the left of -1, which is -1. Since we got different values from the two different sides, we would say it is non-existent or it does not exist. That makes sense to everyone?
So the negative sign is more about like being the opposite of whatever the number is that you're given for the limit as x approaches 0 from the left.
Yep, that's what a negative sign is. It just indicates the opposite of something. That's what it always is, right? I mean, that's what -7 is. It's the opposite of 7.
Yeah, I just always have a hard time because it's like absolute value. I think like no negatives and then you put a negative, but yeah, it means just opposite kind of. Yeah.
Right. Yeah, I mean, and that's exactly right. I mean, it's not making this. It's actually making this positive, right? Because x is less than 0. So, you know, if I'm plugging in -7, the absolute value of -7 is the opposite of that -7 that I plugged in. Yeah, your previous math teacher that taught you absolute value, you know, does you a disservice when they say, oh, absolute value, it's never negative. Well, it's true, it's never negative, but it ingrains this idea in your head that that's all that absolute value is it makes a number positive. Well, there's a little bit more to it. There's a more technical definition of it. So, does that one make sense to everybody now? Everyone good with that one?
Yes.
And anybody else have any other questions on the first half of those? And we'll do the second half on Wednesday. So work on the second half of those by Wednesday. And I could go over any other ones from the first half also if you guys want on Wednesday if something else comes up. But everybody good?
Yep.
All right. In that case, we will move on to what we're going to talk about today. And we finished up, I think, pretty much with separable differential equations. Is that right? We did like a e to the x minus y one. Did we finish that one?
I don't think so.
We didn't do this? No. Oh. Did we do this?
Yeah, that's the one we left off on.
Oh, okay. I didn't realize we hadn't finished those. I thought we had. All right. So let's take a look at e to the x minus y here real quick. So any thoughts on how we're going to solve this separable differential equation? Somehow by separating them, right? But how are we going to do that?
You could do like e to the x times e to the negative y or something like that.
Yeah, or it might be easier to look at it if we wrote it as e to the x over e to the y. But up to you. Right, e to the x over e to the y, that's just exponent rules. E to the, e to the x minus y should be e to the x divided by e to the y. That's just a basic exponent rule. Everybody good with that?
Yeah.
Okay, so now we can separate the variables. We'll bring the e to the y over. E to the y dy equals e to the x, and we'll bring the dx over. So e to the y dy equals e to the x dx. Good or no?
Good.
Okay, and then we will just integrate both sides of it. So what's the integral of e to the y dy?
E to the y.
E to the y. And what's the integral of e to the x dx?
E to the x.
And we need to add a constant to just one side of it is good enough. So we'll just add it to the side with the e to the x. And now we will solve for that constant. So e to the y, right? Y is 2, so e squared. And then e to the 0 because x is 0. And what does that give us for a constant? Our constant should be e squared minus what?
1.
1.
Everybody good there? So we've got e to the y equals e to the x plus e squared minus 1. And all we have to do to solve for y is take the natural log of both sides. And just to be careful with that, because I know that a lot of people get used to, once you do your natural logs with your integration, they all end up being put into absolute values. But right here, we're just taking the natural log of something. So that does not get put inside of an absolute value. And that should be the function that we end up with, y equals ln of e to the x plus e squared minus 1. And then we have to look for any restrictions on the domain of that. But what will we note? We will note that e to the x, this number here is always positive, right? And what about e squared minus 1?
That's positive as well.
That's also positive. So the only thing I can take a natural log of is a positive, and I've got a positive plus a positive inside of there. So there's no restrictions on the domain of this. This should be valid for all real numbers. Good or no?
Do you have to specify the interval of validity if it's negative infinity to infinity, or is it just like assumed if none is given?
Yeah, if you don't put any restriction on it, the assumption is that you are saying it is valid for all real numbers. Now, 8 to 10 years ago, they used to ask for the interval of validity on the AP test all the time on the free response questions. And it's still technically a question that they could ask. But in the last, I don't know, 5 or 6 years, 7 years, I have not seen them ever ask for the interval of validity. So chances are it's not going to matter. You're not even going to need to put it. But it's good that it's good for you to know how to, just in case they happen to ask. They've gone away from it. They haven't done it in almost 10 years, I think. But yeah, the assumption is negative infinity to infinity, if you don't write it. Everybody good there or no?
Yeah.
All right. So the next thing we're going to do, and we'll spend, probably won't take us the rest of the period today, but we'll spend the rest of today's class talking about this, is the basic application of separable differential equations. The only application of these that is required for this class. And that is exponential growth and decay. So I think you're all probably familiar with exponential growth and decay, I hope. And you probably did it in like chemistry class, or I don't know, sometime a long time ago, and they first taught you what an exponential function was, right? And they said something like, oh, you've got 2 rabbits, and after a week you've got 8 rabbits, and then after another week, you've got 512 rabbits, and after and they're just growing exponentially, right? That's exponential growth. Or exponential decay, like how they do carbon dating, they look for the number of radioactive nuclei, and like of some radioactive isotope of some chemical element that's present in something, and they see how much of it is decayed over however many years, and can tell you how old something is. Or bacteria growing in a petri dish, right? That grows at an exponential rate. You're all sort of familiar with the idea of exponential growth and decay, I hope.
Yeah.
Okay, good. So they all just taught you this is what it is, right? If something grows at an exponential rate, that's great. Well, that comes from a separable differential equation. It comes from the differential equation dy dt equals k times y. Okay. And so what that's saying is, it is saying that the change in some variable, so we're looking at y, the change in y is proportional to some constant times y. That gives exponential change. Right? The change in y is equal to a constant times y. That constant could be 1, or it could be, 7, or it could be 0.02. Right? But the change in y is proportional to the amount of y. That gives us exponential change. So the question is why? Well, the answer is fairly simple. This is the differential equation, the change in y with respect to time, dy dt. And so all we have to do is separate the variables and solve the differential equation for y. So how should we do that? How about dy over y equals the constant k dt. Remembering k is a constant, right? K is not a variable. And so everybody good with that separation right there?
Yeah.
Yeah.
Okay. And so now we'll just integrate both sides. That's natural log absolute value y. And what's the integral of a constant dt?
KT.
Yeah, it should be the constant times t. And then we'll add our plus a constant over there, right? Plus c. Well, I guess we should probably go ahead and solve for y, right? How do we solve this for y?
Exponentiate both sides.
Yeah, so e to the natural log of absolute value y just gives us absolute value y, and e to the kt plus c, we can separate that out as e to the kt times e to the c, kind of like we did with a couple of those other problems the other day. Good or no?
Good.
All right, so now this e to the c, this is just a constant, right? I'm going to call it equal to a for now, just so I don't have to write e to the c every time. So I'm going to get a e to the kt. And when I get this out of the absolute value, I normally put a plus or a minus over there, right? True?
Yeah, you usually did, yeah.
Usually we do, right? Well, I'm not going to. The reason I'm not going to is we're talking about exponential growth and decay here. Well, we're talking about the amount of something that we have present. Like we're talking about rabbits increasing exponentially, or bacteria growing, or radioactive nuclei decreasing from a certain amount to another amount. Are we ever going to have a negative amount of those things? We're never going to have a negative number of rabbits or bacteria, right? We're never going to have a negative number of radioactive nuclei. We might get down to almost 0, but we're never going to go negative, right? So we can ignore the plus or the minus that goes out in front of this. And with any luck, that equation looks fairly similar to one that you've used before when you did exponential growth and decay in chemistry or previous math classes. You all seen something similar to that? Maybe had slightly different variables, but about like that?
Yeah.
Yeah, and that's where it comes from. And that's pretty cool, huh? Yeah. So what does A equal?
Isn't it like your starting amount or something like that?
Yeah.
Like in
A,
exponential equations.
right, A is the initial amount, and we should be able to prove that. Right, they always taught you, oh yeah, A is the initial amount, or whatever they might have called it. I think they often do A equals A naught or Y equals Y naught. I don't really use Y equals Y naught. So let's prove that. If I have Y equals that amount, A e to the kt, the only amount that I can be guaranteed to have is I know that when t equals 0, y is the initial amount of y, right? And we always do initial amount as y sub 0. So I know that if t is 0, y is y naught. So I'll just replace y with y naught. I'll put an equals instead of e there. E to the k times 0. And what's k times 0? Should be 0. And what's e to the 0?
1.
Should be 1. And a times 1 should just be a. And so that gives us the formula that you're probably even more familiar with, y equals y naught e to the kt. And that's your basic exponential growth and decay formula. Sometimes we put a negative in front of there. That is just indicating that it's a decay problem. And if there's no negative there, if this k value is just a positive constant, then we have growth. Good or no?
Good.
Aren't you all astounded and amazed at how calculus derives these equations that you've used in the past? Wow. Cool. I know who's not getting a letter of recommendation next year. Whoever just went meh. I don't know who it was though, so I guess you're lucky. Cool. So just kidding. I'm just joking. So like we already went through this, right? dy dt is ky, y is y naught when t is 0, gives us that equation. And we talked k is that exponential growth constant. It'll normally be given to you. So we said if k is positive, it's growing. If k is negative, it's decaying. Probably recall compound interest formulas. They're derived from this same idea. You don't need to know or use these for this class. Just wanted to put those out there. Those are important also. Those come from the same thing. The one little thing that we do want to use this for is figuring out the half-life of a radioactive element. So what we're going to do is, half-life just indicates that half of what you started with is gone. So that would mean that the y value, right, this is normally our y value, is just equal to half of what we started with. And since we're talking about the decay, the decrease in these radioactive nuclei in this element, we have a negative in there because it's a decay. Good or no?
Wait, could you just say that one more time?
Okay, so I'm replacing the y with a half of y naught because we're looking for the half-life. And the half-life of a radioactive element just is the amount of time it takes for half of what you have to disappear. So I'm going to start at the initial amount and I'm going to end at half of the initial amount. That's the definition of half-life. How long it takes half of the stuff to decay. So that's what we've got here. Is we've got the final amount is half of what we started with, and it's decay because we put a negative sign up there.
Okay, thanks.
And so now we should be able to use that to solve for t. We can cancel out the y naughts to get e to the negative kt equals, and then we've just got 1/2. We'll take the natural log of both sides to get negative kt equals natural log of 1/2. And negative kt, and I'm going to write this out. Natural log of 1/2 is natural log of 1 minus natural log of 2. And natural log of 1 is 0. So this becomes negative natural log of 2. And that half-life, t, should be what? Should just be the natural log of 2 divided by k. And so this is an important thing that you may or may not have seen in chemistry class at some point, but this will always give you the half-life of a radioactive element. Natural log of 2 divided by k. Good or no? And we're going to note that k is always a positive constant. K is always a positive constant. So when we're given the differential equation, dy dt equals negative 0.3 y, the K value is just 0.3, and the negative sign indicates that it's decaying. If it was 0.3 y, then we'd have a K value of 0.3 still. And since there was no negative, we'd indicate that it was growing. So
Are we gonna be, I have one quick question.
Yeah.
Are we gonna be using like all these equations that we've just derived like in our like upcoming worksheets and like our units, or is this just like background on exponential stuff?
It's just background on where it comes from, basically. The whole point of it all is just for you to know that if you have the differential equation dy dt equals k times y, that's exponential growth and exponential decay. You're not going to have to solve exponential growth and decay problems per se.
Okay.
Yeah.
Okay.
All right. So this is the one problem here that we are going to do real quickly, which is we're going to figure out the half-life of samarium 151, which is modeled with this differential equation, dy dt equals negative 0.0077y. So the negative indicates decay, and the 0.0077 tells us, or 0.0077y, this is tells us that it's a decay, with the 0.007 equaling our K value. So if we want the half-life, what should the half-life be? It should be the natural log of 2 divided by K. Doesn't get much easier than that, probably. And what do we get?
I got 90, pretty much 90.019.
Oh, good. You're going to round to at least 3 decimals. Always round to at least 3 decimals. And that's it. Any questions on any of the stuff that we've done today?
Wait, how did you get T again?
T was the natural log of 2 over K from the slide we just did before it.
Oh, okay. Oh, I see. Okay.
Right, this was the half-life, right? And that's what this was asking us for.
And
Oh, okay.
Good.
in the equation where you had like the negative value and you're like, this means decay, is that just like part of the conventional equation or something like that? That if it's negative out front, it means decay instead of growth or something?
Correct.
Okay.
That's what we were talking about back here, right? K greater than 0 is growth, K less than 0 is decay. So if they throw the negative in front, it's decay. Even though the constant is still a positive constant, K, which I think I wrote somewhere. I think I might have erased. No, K is always a positive constant, but they put the negative in front of it to indicate decay. Good or no? Any other questions?